under this curve, over the interval where x is in between 1 and 5, using 12 right endpoint rectangles. And they're right endpoint rectangles. So the way that the book taught you was they would show you what the curve looks like, and then they'd show you how you can draw little bitty rectangles underneath the curve. And so because it's a right endpoint rectangle, I'm looking at these points. There's the height. There should be 12 little heights of each of the 12 rectangles. And the top right corner of each rectangle is touching my curve. But you might wonder, how did I know how to draw it, and how did I get my rectangles in there? So the way you figure it out is you look at your interval, it's between 1 and 5, and you know you somehow have to get 12 rectangles in there. So you go 5 take away 1, which gives you 4, right? Because there's like 1, 2, 3, 4 spaces that you have to divide up evenly into 12. And then so you go 4 divided by 12, and that gives you 1/3. And I was going to call it 0.3 or 0.33 or something, but I think that it's best to just leave it as 1/3, which makes calculating this by hand really hard. So basically, here's the concept. We know that rectangle is length times width. So I could get the area of this little rectangle by going 1/3, because these are all broken into 1/3. You can count them, there's 12 of them there. 1/3 times the height. Well, I know the height of my graph is like 10, and oh, how did I know what this graph even looked like in the first place? Well, it's an upside down parabola, and I did put it in Desmos just to make sure what it would look like, and I'll show you my Desmos in a little bit here. But basically, it's the width or the base times the height. If I want the height of this first rectangle, well, the height is on the curve, so I would have to use this point, which is 1 plus 1/3. This is 1 1/3 right here. If I plugged 1 1/3 in to this ugly function, I would get the height of the rectangle. And I actually did. I plugged it in, and then I saw that you don't want to plug in, for the second rectangle, you'd plug in 1 2/3 right there. So you'd have to square 1 2/3, multiply it by 1/2. So you'd have to plug all these numbers into here, and they're fractions, and it's horrible. And then you would have to add up all the areas of all the 12 rectangles. So when I looked in your answer book to see how they would want you to do this, I saw that they used some summation notation. So let's go to Desmos, and I'll show you what I did to solve this. So you should be able to see my Desmos now. The first thing I did is I wrote the function up here, and then I just plugged in my first number, which was 1 1/3. And so now that's the area of the first little bitty rectangle. But I'm not going to, and I could have just wiped that out and then put 1.66666 and 1.666, and I could have got the second rectangle. And then I could have just erased it and put in 2, and done it for every single rectangle. If this would have been 5 rectangles, I might have done it that way. But for 12 rectangles, it's too much. So I tried to figure out how to get the computer to do it for me. And so what I ended up doing, I'm going to flash us back to my paper. What I ended up doing was trying to figure out how to get this, like this is just what the answer key gives you. And I understand this. There's 12 rectangles, so we're going to add up the first rectangle, the second, third, fourth, fifth, all the way up to the 12th rectangle. So that should make sense. The 1/3 stands for the width. Because I don't know if you realize this, but if I were to get this whole list full of numbers just by plugging them one at a time into here, once I add them all up, I'd have to divide them by 1/3 because it's 1/3. The width of each one is 1/3. Or I could go 7.35 times 1/3, and then I can go the next number times 1/3, and the next number times 1/3. But it's easier to add up all the numbers and then multiply them by 1/3. So what I do is I'm going to take the 1/3 and put it outside my summation. So I want to add up all the numbers first and then multiply them by 1/3. So I ended up taking the 1/3 out, and then, well, f of 1/3 n plus 1, where on earth did the answer key get that? Well, that's how I got these numbers, is I'm going up each time by 1/3. So it's kind of linear. I'm counting up by the same amount each time I'm counting up by 1/3. So it's kind of like y equals 1/3 x plus b or whatever. So let's try 1. So does this work though? Can I put in, like, I know that my first term has to be 1 and 1/3. So I can go 1/3 times 1, times 1, yeah, is 1/3 plus 1. So that works. So this thing right here, the values are generated by adding 1/3 each time. So this thing is basically going in here, in here for my x. Because my x changes by 1/3 each time. So we're going to use this to generate our x terms, so that I don't have to go into Desmos and like delete the first x term and then add 1/3 to it and put it in again. Like, the computer will do this for me. So I have to input 1/3 n plus 1 into f of x. Well, f of x is this gnarly thing. So basically I'm plugging 1/3 n plus 1 in here and here. And that's what I did down here. F of 1/3 n plus 1 is just that original function, but everywhere there's an x, I put a 1/3 n plus 1. And I actually typed that into Desmos. I typed this whole long thing into Desmos, and it gave me the right answer. So let's go back to Desmos, and I'll show you. So this part right here came from the fact that my table went up by 1/3 each time. It was getting bigger in a linear way. So this is how we generate the x terms, all 12 of them. And then you can't see it, but maybe if there's a 1/3 right here. So I'm multiplying the whole thing by 1/3. And then the computer, how did I do this? I just went over to functions and I hit that summation, and it allowed me to put the 1 and the 12 in. And then I just typed my function in. And that's actually the answer right there. It's 29.219. 29.2-ish. And that's all I got.